of this cosmic ray physics to an archaeological problem. I'm not an archaeologist, I'm like you, a physicist, but as you will see, physicists can help in many ways society, and I'm going to describe to you this particular application. So I begin my presentation. I don't know if you hear me well. I noticed in the presentation that if you get too close, then it distorts. So I will try to do my best not to make the best use of this equipment. So I begin by describing to you the IPHO40. Is actually, UNAM is Mexico's National Autonomous University. UNAM is the largest university in Mexico and must be one of the largest in the world. We have about 300,000 students registered. That's almost, that's an enormous number. And UNAM is, for Latin American standards, is ranked in this international rankings of universities, is ranked to be the best university in Latin America. So I'm very proud to work in that university. We have a physics institute, and that is the IPHO, the Instituto de Física. And so the work that I am doing is actually carried on under the support of the IPHO40. Now, when I talk about particles and astroparticles, I'm going to have to make some definitions, and this is where my talk starts. So the next transparency, please. There. I tell you the concepts in the beginning are rather trivial, but I really don't know how much you know about these things. So I wake you up and the thing gets more complicated. Now, as everybody knows, the structure of matter, you can just get deeper and deeper into matter, and you know that matter is made out of atoms, which have nuclei there are collections of molecules that are collections of atoms, and then those atoms are made out of electrons and a nucleus. And if you look further, you can see that in this particular case, hydrogen, a nucleus is made out of quarks. That's a proton, actually, is made out of quarks. So this is the basic structure of matter. The electron, which I missed in this description, belongs to the same category as the quark. And this is called the standard model. The building blocks of matter are described in this figure. The whole of matter is made out of this Lego type thing, in which you have 6 quarks and 6 particles which are of the same nature as the electron. Okay, the quarks, the up quark and the down quark, together with the electron, form the vast majority of the matter that makes the universe. The other particles are unstable, and so they have been observed in the laboratory, but we know that they are just part of the building blocks, but are seldom necessary to describe the macroscopic physics of the world. The electron has it belongs to a family that also has these heavier relatives of the electron, the muon and the tau. I'm going to be using the muon later on for this application of the theory of the sun. Just the muon is like a heavy electron, and the tau is just it's an even heavier electron. And together with these three, you have these neutrinos, which are these elusive particles, which are light. For some time they were believed to be massless particles, which somehow are characterized by being insensitive to what is called the strong force, the strong nuclear force. And as I described before, the quarks are these 6 particles, and these 6 particles are joined together by a force that is called the strong force, and is carried out by a field called the gluon. Okay, and the gluon is, as the name already implies, is a particle that somehow helps these guys together. The photon is also a bonding force between these type of systems. So that is the bonding force that keeps the electron around the proton in this particular example that I chose. And there is a third force at the nuclear level that I did not mention, and I'm not going to be describing or talking about it very much, which is the force that is called the weak force that is carried by the Z and the W, which are very heavy intermediate bosons. So this picture is what is called the standard model, and one peculiarity that I didn't mention is that the quarks, nobody has ever seen a free quark. So the quarks are something like a successful theory. Everybody believes that quarks exist, but nobody's ever seen a quark. And apparently the quarks don't really like to be seen. The quarks carry a property called a color, but nobody's seen a color particle. That means that they join together to disguise their color in twos to form mesons, and in threes to four baryons. The baryon, the proton is the more stable baryon. Okay, so I guess I described all what you need. If this you know, then we can carry on to the next one, please. The next one, please. This guy is not. There we go. So we can also. I am repeating here this scheme of the basic particles. And one thing that was discovered long ago is that every particle has a partner in nature, and this partner has all the properties, all the same properties as the particle itself. Let's say the up quark has this particle that has a bar on top, and is similar, it has the same properties, and the magnitude is all the properties are the same, except that it has one of its properties, generally electromagnetic property, reversed, like let's say the electron and the anti-electron, which is called the positron, have the charge reversed. One is positive and the other one is negative. And when you put together an electron and an anti-electron, what happens is they annihilate, as we see represented in the next transparency. The next transparency, I said. Hello? There we are. So, you have this recipe in which you can actually, if you put together a positron and an electron, they annihilate and produce light. This is a phenomenon that is commonly, you describe it using the Einstein's famous equation, which you can have matter equating energy. So E equals mc squared somehow is basic to understand this process. The next transparency, please. There is another recipe in this thing, is that, as I said, you can take particles and anti-particles to create energy. But another part of this recipe is that if you have energy, you can, out of energy, you can create particles. So you can gain from energy, create matter. The only part of the recipe that you have to respect is that you can, if you create matter, you have to create antimatter at the same time. So in a way, this is a very neat idea in which you can go from matter to energy and from energy to matter, and you always conserve some quantities, which are quantum numbers are called, and these quantum numbers somehow force you to go through this recipe of going from pairs of matter, antimatter to energy, and then reverse. So all these things is connected. The next one, please. So now I'm gonna this is the next one, please. Now, another concept that I'm gonna be dealing with in this talk is related to cosmology. And you may have seen this many times. I guess now, even in kindergarten, you have this description of the line of life. I don't know how it's called, in which they describe the life of the universe in a coordinate. You have the time scale here. We live somewhere somewhere here. This is like 12 to 15 billion after the Big Bang, and we are told that the universe began in a singularity some long time ago, and nobody really believes. I mean, this is a very speculative part of the physics that happens here. But what we know, and we are able to understand now, is that at some point this matter, this energy that was dominating the early universe, eventually created quarks and anti-quarks and gluons and so on, and the electrons that were lying around. And then you create this type of matter that is described here as a quark soup, okay? And this quark soup, if we were able to look at it, you will see it's a beautiful medium in which you have the color, you can see the color of the quarks. Now, as I told you, in the laboratory we've never seen color quarks, so eventually if the universe expands further, it cools down to a point where quarks have to unite into mesons and baryons, and somehow that is described by this line here as a freeze out. The freeze out means that once the universe cooled to this point, then all what is left here are baryons, that's the proton and the neutron, and another heavier if they exist. I mean, if they are left over are very, very unstable. Anyway, most of them are neutrons and protons, and electrons, and neutrinos and so on. So this is more or less where the picture. There is another transition here which is not marked in this picture, and that is going to be important for my talk, is that eventually these baryons combine, the proton and the neutron combine to form a heavier, lighter nuclei, light nuclei like deuterium, like helium and lithium, and these early nuclei are described by a model that is called the Big Bang nucleosynthesis that I'm going to be describing in the next transparencies. Anyway, after some time, this is a long time, 300,000 years later, the temperature of the system is so low that the photons are no longer able to ionize the atoms that were formed here. So the electrons are captured and the universe decouples. That means the photons and the matter is decoupled, and the photons just run free through the universe. And this is what forms the 3-degree Kelvin background, and something cosmic background that you might have heard in some other talks. Anyway, I'm not going to describe the astronomy in this part, which is not relevant to my talk, but I'm sure this description has been given to you some time before. Now, some of you that have listened to me describe this thing, and I'm sure you heard this description many times before, may have asked yourself, the next transparency, please, and what happened to the antimatter? Okay? Because I've been telling you that matter in the laboratory is created at the same time. Well, you cannot create just matter. If you have energy and you create matter, you have to create antimatter at the same time. So, did the universe, I mean, what happened to the antimatter? Okay? Did antimatter evolve just like matter? And there is some place, an anti-Yucatan filled with, an anti-auditorio filled with anti-students listening to an anti-speaker or something, or whatever happened to the antimatter. Well, nobody really knows. What we know is that there is not enough antimatter for us to, astronomers have looked for antimatter and they don't find much antimatter, at least in the visible universe. And this is an open question. This is a question that has not been solved, and this is going to be part of my talk later. Next one, please. In these previous two cosmology pictures, there was a transition between the quark soup. You remember there was this quark soup, and the baryons and the mesons. This is called, this phase transition is called the atomisation. And this phase transition you can create it by several ways, the Big Bang being one of them. But since my talk is going to be concerned with trying to recreate this physics in the laboratory, you can imagine that if you possess an apparatus that gives you this possibility, if you can compress matter to absurd values, you can actually recover the creation of this soup. Or else, if you warm it to a very high temperature, which here is measured in MeV, and MeV is 1,000,000 electron volts, and an electron volt is the energy of one of the photons that are illuminating this screen. So somehow at 150 MeV of temperature, there is this transition that is called the hadronization of matter. So here you have the soup, the quark soup, and down here you have the hadrons, which form the protons and the other particles that I described before. Now I want you to note two things, two labels here. One of them is early universe. So I have been described to you the universe in this sense, that you go from hot to cold this way. And a way to reproduce this is now being attempted at an accelerator that is being tested at CERN, which is this international laboratory near Geneva. It's called the LHC, the Large Hadron Collider. And in this, we have proposed an experiment that I'm going to describe to you later on, by means of which we want to understand this hadronization process and something around that. The next one, please. I will go back to what this hadronization, how this hadronization is described by cosmologists in the Big Bang. And this is actually taken from a Scientific American paper. And they describe this thing in 4 pictures. Here you have the quark gluon plasma, what is been described so far as the soup. And then somewhere here you have the hadronization. It's not really described how it happens, but from here to here you have color. Here you only have protons and a few neutrons. You know that the neutrons, the free neutrons are unstable, so the neutrons are scarce, and in a ratio, it's told by the Big Bang nucleosynthesis, in a ratio of 1 to 7. So somehow you get many protons and a few neutrons. Now it turns out that protons and neutrons love each other, and they get to form couples rather easily. They are sticky, okay? And so they form these particles that are called neutrons, which are heavy hydrogen nuclei that have a proton and a neutron. And these deuteria happen to be even stickier among them, so that if you left them together for a little while, they form the heavier element called helium, the isotope helium-4. So this is more or less the sequence how the Big Bang nucleosynthesis describes it. You go from the color soup to the early elements formed after the Big Bang. The next one, please. Needless to say that there are very few heavy nuclei formed. I mean, the sequence somehow stops in this here. Now, this is a picture that is taken from a paper, from a Big Bang nucleosynthesis paper, and this is a picture. I don't know if you see the curves, but I go through them rather quickly. In the horizontal axis, you have temperature, so the universe cools this way, okay, and time grows this way. So I have put a time scale here and temperature here. So as the universe cools, you see it takes this time to cool. And what is being plotted here is the relative proportion of the different particles that I've been describing to you, how the proportion of them changes as a function of time. So in the beginning, you see these are protons, the black line, neutrons are the red line, and here is the deuterium. I'm gonna be using later on helium-3 and other particles, and this is helium-4, the green line. Anyway, in the beginning there were equal numbers of protons and neutrons, and by the time they get to this ratio of 1 to 7, you see the neutrons decay forming protons, so this line goes up a little bit. This is a gross logarithmic scale, and so is this one. So in a way you see the protons grow a little bit, the neutrons drop a little bit, but you can see that the deuterium is actually decreasing in the beginning and then grows up rather fast. And as it grows up, helium-4 grows up even faster, which is what I told you. If you form the deuterium, then helium-4 uses all the deuterium and somehow gets to form, in the end, to form the largest fraction of the matter in the universe, as you will see in the next transparency. I will come back to this transparency because this is a field in which I'm right now working at in the project for the LHC. So I just leave you with this picture. One thing about this picture that I want you to see is that somewhere here is a very well-defined proportion between protons, neutrons, and deuteria and particles with mass 3 and the rest. But here, something very drastic happens, and then this thing changes. This is what is called in one of those previous pictures. Well, it's the label that I told you was missing. This is the element freeze-out. So this proportion of protons to helium-4 and to deuterium and all the behavior are actually are defined in this instant. And some of you, because you are physicists, may have heard of this famous book or even read this book by, which is called The First 3 Minutes. And these are the first 3 minutes. This is what happens here is rather dramatic. And after these first 3 minutes, nothing really changes. 300,000 years later, just these protons and helium-4 somehow capture electrons and they are left forever. Another thing that is peculiar of this picture is that the green line here, there is no known source of deuterium in the universe. What happens is that this deuterium, the ratio of deuterium to helium-4 and protons is more or less freeze out in this instant here. The next one, please. So how do we know about all these things if it happened so long ago? Well, there is a combination between two sciences which are very related, as you're going to see, which is astronomy and cosmic ray physics. They both depend on observing information that comes from the sky, okay? And of course, astronomy is based on observing photons. So the emission of photons or the absorption of photons from celestial bodies give you information about these elements that compose stars or very peculiar objects in space. And but all these systems, stars and exploding stars or these quasars were described to you the day after yesterday, before yesterday, sorry. All these systems are nuclear reactors that emit energy, emit light, abundant amounts of light. And this light somehow is detected by astronomers, but they also emit the matter from which they are built. And so this matter flows from these stars, flows away and forms the cosmic rays. Now, matter that is flown away from these objects is charged hydrogen and helium and other nuclei. And these particles, because they have charge, electric charge, when these particles travel around, they actually are sensitive to the magnetic fields at all scales. You know that the Earth is a magnet, and so is every single celestial body. So somehow, if one of these objects emits a charged particle, and this particle is going to be detected on Earth, the only thing you will imagine that this particle travels from one place to another, being deviated by all the objects that it bumps around. So what happens is that it's sort of like a cosmological pinball in which this particle flies, goes near the next star, and then it bends, and then goes near the following star and bends the other way. And by the time it gets to Earth, you are not going to be able to tell where it came from. So the difference between cosmic ray physics and astrophysics is that you can only tell by the relative composition of the particles of these residues. You can tell a little bit about the physics, but you cannot tell where they come from. Whereas astronomers can tell a lot more. One other complication of cosmic rays is that they are very energetic particles, and when they reach the top of the atmosphere, the Earth's atmosphere, they interact with the particles of the atmosphere. They have so much energy that they can create other particles, and so they generate what is called cosmic ray showers. And so some of what we know of cosmic rays is by placing detectors on the surface of the Earth and trying to understand what this particle was by the residues that were left. Okay, the next one, please. Now, what have we learned, grossly speaking, from these two? You can actually compare them, and believe it or not, there are astronomers who spend their lives counting the matter in the universe by looking at every star and noting someplace in a notebook how much hydrogen and helium and whatever they find in different stars. And they add all that together. This is an ugly picture, but you don't have to understand many of the details. And they add all together, and so they compare the relative abundances of elements. You know that elements are labeled by this, the atomic number. The letter C is used, which measures somehow the amount of charge that they have. So that these two guys here are the helium, the hydrogen, the helium, the lithium, and the beryllium and the boron, and so on, so on. This picture ends up in iron somewhere here. And what you can see, and the field circles here, that's the universe out here, is what astronomers tell us the universe is made of, all stars are made of. And the field circles here is the cosmic, what the cosmic ray physicists detect in their detectors. And you can see overall, they more or less follow the same trend. In this picture, they were normalized to this element, which is carbon. So you see that, for example, in both pictures, even though these two are very separated, hydrogen is far more abundant than helium, and then lithium is way down here. This is a gross logarithmic scale, so these things, and so by the time you get to carbon and the others, this thing is rather flat, although it changes by some orders of magnitude, it's rather flat. So most of the universe, 90% of the universe is made out of protons. The 90% of the rest are helium, nuclei, and from then on you have a little or very little lithium and some carbon and so on. So that's more or less the picture. The difference between the two come from the fact that cosmic rays travel, the cosmic rays we detect on Earth, before they reach Earth, have traveled such a long distance that along the way they have suffered interaction with other matter they find around, and so they somehow break apart, and so the population of different particles is somehow shifted. This is what makes the overall, you see there is a far more lithium in cosmic rays than what is observed in stars. But the rest more or less follow the same trend. The next one, please. If one wonders what is the energy of these cosmic rays, you end up with this plot. This is the flow of particles on the near the Earth surface. Okay, well, near the Earth. This is the flow the flow of particles, and this is the energy in a gross logarithmic scale. And what you find is that if you add up all these cosmic rays and you only measure the energy, what happens is that you have a rather monotonical curve like this, in which the most abundant particles have low energies, and then as you increase the energy, they just get less and less and less abundant. This is again used in the scale is electron volts, but something you don't see here is that this scale ends up in 10 to the 20. Okay, now 10 to the 20 is a number which is actually bigger than the Mexican foreign debt, so it's a big number. But anyway, it's a rather featureless curve, but it somehow, since some time ago, it has caught the eye of physicists that it has a kink around here that is called the V. Okay? Now I just read some of these labels to you. At this scale, you have one particle per second, per meter square per second. Okay? Around here, you get one particle per meter square per year. And down here, around here, you get one particle per kilometer square per year. So you wonder how these points were measured, okay? And these points were measured with really very large detectors that cover hundreds of kilometers or square kilometers. Anyway, this picture it tells you a lot about. I mean, you have to model it, and you use models in which you model the acceleration and the transport of the cosmic rays from the point where they are created to Earth. Then there are models which successfully reproduce this curve. This is still something that nobody really knows why this kink is there. There are theories about it. And one of these models, one of these theories says that the particles since these are all the cosmic rays, so you can actually have the possibility that there may be a different law for different elements that may be causing this kink over here. And one of the projects that I'm going to be describing to you is actually aimed at trying to find this out. The next one, please. You got it? So that was the basics of my talk. Now these three are going to be rather fast, and I will concentrate. The last third of my talk is going to be the Pyramid of the Sun project, which I will describe later. Anyway, the projects I'm involved with, or my group is involved with at UNAM, is involved in trying to respond to these questions. Where is the antimatter? Does relative abundances depend on energy? This is what I was talking about in the next plot, and then in just the previous plot, see? And the other thing is whether one can study or reproduce these phenomena in the laboratory. And this, as I said, the next one, please. So these are projects. The first three are international projects. The first one is called alpha magnetic spectrometer. The alpha magnetic spectrometer is a magnet that has been built to be installed on the International Space Station. And of this project, we have contributed, as I'm going to describe soon, a piece of equipment. CREAM is cosmic ray energetics and mass. This is another international collaboration in which we fly a balloon at the South Pole, and this balloon has from this balloon hangs a detector to which we also contributed to construct. And the purpose of CREAM is this business of trying to see if there are different laws for the different elements. The third experiment I'm going to describe briefly to you is called ALICE, a large ion colliding experiment, and is described by this picture. It's just an enormous particle detector that is placed on the beam line of the LHC, the Large Hadron Collider. And last, and which will be the last step of my talk, is the Pyramid of the Sun detector. Here is a picture of a Mexican journal which they represent us trying to see what's wrong with the pyramid. The next one, please. So, search for antimatter in the universe is a project that was proposed by this fellow here. This fellow here is Samuel Tink. He's an MIT professor who won a Nobel Prize for having discovered one of those 6 quarks that was described before, the charmed quark. And this is my group, this guy in our laboratory at the University of Mexico. You see, this is a description. You're not going to see many of the details, but this is a description of all the universities. There are 56 universities and almost 500 collaborators. And you see, this is a map of the world that's somehow truncated, so Mexico gets chopped off. But you can see Mexico somewhere there. And if you had powerful enough eyes, you would see Mexico and you would see Yunnan here. Next one, please. What does this AMS detector is? Well, this, apparently we're having problems. Well, the AMS detector, I hope this fellow wakes up and recovers. The AMS detector is a magnetic spectrometer. A magnetic spectrometer is really just a magnet. It has the size of a washing machine, a little bigger, okay? And it has a dipole inside. So, the way you can differentiate matter or nuclei from anti-nuclei is that nuclei have positive charge and anti-nuclei has negative charge. So if you let nuclei go through a dipole and crossing the magnetic lines perpendicularly, you're going to see that matter curves one way and antimatter curves the opposite way. I hope we recover from this because the rest of my talk is going to be totally screwed up. But anyway, so this magnet is what in the volume of the magnet is filled with detectors that track the trajectory of the particles along the way in order to tell you if the particle travel having a curving one way or the other way. Also, you need to know in these particles other properties of these particles. What is their Z, the atomic number, and what is their speed, and other properties. So the detector itself has 300,000 detection units. And among these 300,000 detection units, if the picture ever comes back, you will find that there is a little piece which was built by a French-Mexico collaboration with the University of Grenoble and our university. The concept here is that when I describe to you the universe and I tell you there is antimatter missing someplace, there are 2 possibilities for this, the missing antimatter. One possibility is that antimatter somehow, well, matter and antimatter were created in equal amounts, but they very nearly annihilated each other. But somehow, the little bit that remained because of fluctuations, the little bit that remained of the matter is what forms us, and a little bit of the antimatter somehow ended up in another part of the universe. If this antimatter ended up in the other part of the universe, we couldn't tell. I mean, if it evolved in the same way as matter, then it would have formed stars and which emitted light. Astronomers cannot tell you about this light. From light, they cannot tell you if you are looking at an anti-star, because the light emitted by the transitions of an electron in an atom is identical to the light emitted by a positron in an anti-atom. It's just the same light because it's the same transition. So the light that you see in the star down there in heaven, if you just look at the light, you're never going to be telling if that star is a star or an anti-star or an anti-star. So I often make the joke to this, when there are ladies in the auditory that, I mean, we men, at least Mexican men, are always offering to take down the star from our pretended companions. And now what I tell these ladies is that be aware that they may be looking just at an anti-star and be, if they bring the anti-star down, everybody's gonna disappear. I'm making all these jokes which we're trying to record, waiting for this picture to come back. And I hope, I really, this is complicated. Why don't you just do click? That's the one. In order to talk about the pyramids, I need, now there it goes, I need my pictures. Now, there it comes. Well, I guess you're going to appreciate after this comes that doing physics in Mexico is not a trivial thing. If you had to do physics in a chaotic environment, but that's part of it. So now here we have I was telling you about this magnet, the dipole, and how this dipole is filled with detection units that allow you to track particles, whether the particles curve one way or the other way. And if they curve one way or the other way, the tracker is going to tell you that you are dealing with matter, anti-nucleus or an anti-nucleus. If we were to detect a single anti-carbon in this experiment, that would definitely state that there is an anti-star someplace, because an anti-carbon cannot be created by any other means. So, but you cannot do these studies unless you put your detector away from the atmosphere, okay? Because otherwise, an anti-carbon that reaches the top of the atmosphere will just annihilate. So you have to place the detector on a satellite, and this is why this thing has to go on the International Space Station. This is, I was telling you, the bit that we constructed together with our French colleagues. The next one, please. Hello. Maybe I'm going to skip. It's just describing you the type of our contribution is that our detector is called a Cherenkov ring detector, and this Cherenkov is a peculiar effect in which a particle that travels through a transparent media of that has an index of refraction bigger than that than 1, then that particle will somehow produce light in a cone, and the opening angle of this cone is somehow related to the velocity of the particle. So this thing ends up helping you measure the velocity of the particle. And in Mexico, we characterize the material out of which these cones are produced. The next one, please. This is only an equation, actually. The detector actually flew in 1994 in the Discovery shuttle for 10 days. So we were actually allowed to go only for 10 days with our detector, and we were able to understand a little bit of the physics of cosmic rays. We didn't detect a single anti-nucleus, but what we did see is that we could tell we could reproduce the spectra of cosmic rays just in these 10 days very adequately. I don't have time now to describe our findings, but I'll tell you just briefly that apparently cosmic rays, when they reach the Earth's surface, they produce something, I don't know, I think it's called skipping, when you throw a stone in a lake and it bumps several times. Cosmic rays, actually, when they reach the Earth's atmosphere, they lose energy rather rapidly and are able to bump back and so that they can cross the detector again. And so you see the spectrum that I described before, and a little copy of it, which are the particles that went the bumped ones. The next one, please. And of course, I was telling you that next year the detector is already built and waiting at CERN to be transported to the Kennedy Space Center, and from then on, NASA will take over it until it's launched. The next one, please. So now I describe to you the CREAM experiment. Just to remind you, the CREAM experiment is to try to investigate a theory that describes this kink in this curve. And to do that, in order to do that, we built a detector that looks like AMS, except that it doesn't have a magnet. And we also, this is also in collaboration with this French group. In this case, it's only a balloon. The balloons are launched in Antarctica, and they turn around Antarctica. They are launched in a NASA station that is called in a place called McMurdo, and they go around the South Pole due to a peculiar vortex condition that occurs in the early summer in the South Pole. The next one, please. The next one, please. There. Okay, so the detector is just a description of the detector, and guess what? It has a Cherenkov detector, and the Cherenkov detector is amplified here, and this part of the Cherenkov detector was characterized by Mexicans, they say. The next one, please. There. And you have some photographs of the group in Antarctica. Here's the mapping of the orbital. This is when the detector was just launched. Okay, the detector is this big thing, and well, there's some photographs of the group. The next one, please. This happened just last December, and it was recovered in January. This is what we observed. Now, the curve that I was describing before, the curve that has been shown to you twice, is now decomposed by elements. This is what this detector does. So you have the protons and the heliums and the whatever, down, until the iron, okay? And you see, it has been measured by us and by AMS too, this is CREAM, and the pink ones are the CREAM data that we have measured. And you can see that we have filled up a gap, and there are other detectors that have also contributed to this. This is a very competitive field, so we are measuring, and there are other people also measuring. But anyway, you can see that we have filled up the gap. And what is important is that although we have not gotten, the kink should occur in this part, but we have already realized that these curves are all parallel. So it's very difficult to explain the kink by saying that one of these has a different slope, which is what I was trying to argue before. So that model that says that the different elements could have a different slope is not the explanation. The next one, please. Now, can we test this? Can we test the cosmology in the laboratory? Well, of course, you need a big laboratory, and for that, we are using the LHC. The LHC is the largest accelerator in the world. You may have heard of it last year because it actually failed to start. It was inaugurated, and about a week later, it failed to start, and that made an international scandal. And those of you who don't follow scientific scandals may have also heard of it because Dan Brown wrote this novel about the angels, or whatever. I don't know how to. I know the name in English, in Spanish, but anyway, you may have heard of that. Anyway, all that happens here in this accelerator. It has 27 kilometers perimeter, and this accelerator is full of superconducting magnets that guide the particles that are injected on it. It has 4 main experiments, and one of them is called Alice, which is around here. This is just a picture of the French-Geneva border, French-Swiss border, and the detector. So the next one, please. The next one, please. Okay, this is our detector. I already described before. I showed you this picture before, but I just tell you the beam line is actually here, so particles come from this side and from this side, and Mexico has contributed with this piece of apparatus called D08 that I have drawn here in white for you to see. Basically what happens as a detector is that particles are made to collide in the middle of this detector, and this detector has a whole bunch of tracking devices, and then they repeat the same show as the AMS. You track every particle, and then you can tell its energy, its nature, and so on. The next one, please. Of course, the aim is to try to reproduce the quark-gluon plasma in the laboratory. This is the V08 detector being built, assembled in Mexico. Note that there are female physicists in our group in a proportion which is larger than the competitors in these Olympic Games. If you count here, you count 20% of females in our group. I said that because the president of the Mexican Academy of Sciences was complaining that physics is a macho type science, but it is. So, I think it's true, but we Mexicans are famous for being machos, but apparently we are not as machos as others. The next one, please. What we want to do what we have proposed to do in the LHC is actually to measure the amount of deuterium and helium-4 and helium-3 and tritons and other that are produced in the hadronization at Alice. Okay, this is not the first time that this thing is going to be measured, but this is for sure the first time that is measured once we are sure that the quark-gluon plasma has been formed. This is a plot now by human beings, and of course I'm going to describe to you another use for cosmic rays. This is the pyramid of the sun in Teotihuacan, which is near Mexico City, some 40 kilometers away from Mexico City. You may have seen this picture before because it's somehow it's a famous pyramid. The next one, please. I will describe first to you very briefly the problem. The pyramid, here I am representing schematically the pyramid. The pyramid it was built 2,000 years ago by the Teotihuacano people. The Teotihuacano people were contemporary of the Mayans, but they have one problem, is that the Teotihuacano didn't have a written language. And so they left very beautiful monuments, but nobody really knows what the monuments were built for. And so archaeologists have been digging through the pyramid of the sun, which is the largest pyramid in Teotihuacan, and they have been digging tunnels to try and test a theory that says that the pyramid of the sun may have been used as a burial place, as a burial monument, just like some of the Mayan pyramids and indeed some of the Egyptian pyramids. But at different stages they have dug tunnels and they found nothing. The last one was done in 1968 around here. So the Anthropology Museum didn't grant any more permissions to dig the pyramid because they were going to make out the pyramid like a Gruyere cheese filled with holes. And so the condition now is that nobody's going to be able to dig a tunnel in this thing unless they are pretty sure where to dig. And one other thing that you may want to know is that in the 1970s, there was discovered that this pyramid has a tunnel running 8 meters below the base of the pyramid. The next one, please. And this is a very peculiar tunnel in the sense that its entrance coincides with the face, the front face of the pyramid, and although it's all crooked, somehow it's parallel to the pyramid and it ends up near the symmetry axis of the pyramid. So here I represent it again, and here is where we have our laboratory installed. The first picture of my presentation was actually my group sitting in the laboratory that is in here. This is this is a source of the speculation that I'm saying that actually the current theory is that the pyramid, that this place was so magic and so important that the pyramid was built on top of this magic column. The next one, please. But still, for physicists, this is how the cave looked before we installed our laboratory in there, and this is just this place is considered so magical that the ancient codices describe this type of caves, which are caves with little holes or little spaces around, are described like Chikomostok, which is the place where the gods are born. Next one, please. We are by far not the first ones. Well, actually, we're going to be the second ones to use the experiment to test pyramids. The first experiment was carried out by Luis Alvarez, a Nobel Prize from Berkeley, who was actually the one who proposed that the extinction of the dinosaurs was produced by the fall of a meteorite that was described to you on Monday. So he's the same fellow, actually. This is not, he's actually was not Mexican, he's already dead. He's not Mexican, but he was of Spanish origin. He refused to speak Spanish. I actually met him because he was a professor he was a researcher at the Lawrence Berkeley lab when I was a postdoc there. Anyway, his experiment, he faced a similar archaeological problem. There are three famous pyramids in Giza, Cheops, Kefrem, and Miserino, and he researched on the Cheops pyramid, and he used the fact that the Cheops pyramid has a chamber below to try, the Cheops pyramid is known to have an internal structure, but the Kefren is only have this chamber here. So he installed his equipment in this chamber. This looks like a flash Gordon type equipment because it happens in the 60s, okay? Maybe you don't even know who flash Gordon is, but these are films that were very peculiar. Anyway, this is his experiment installed in this, and he proved with this technique, by detecting cosmic rays going across the detector, across the pyramid, by detecting cosmic rays, he proved that there is no hidden chamber in the Kefren pyramid. The principle is very simple. Cosmic rays are very muons, are the leftover particles from cosmic rays interacting with the atmosphere. And these muons are very penetrating particles, so much so that they go across a pyramid and can be detected in the middle. This is a very tall pyramid, 160, 112 meters. And of course, not all of them go through, and you can, some of them get absorbed, and you can relate the amount of cosmic rays that get absorbed by the body of the pyramid to how much matter they travel. And that's exactly what you do in an X-ray. They shine on you an X-ray source, and they put behind you a photographic plane. And if some of the X-rays go through your body, but some of them are absorbed by the inside of your body, and you can map the density of your internal density of your body just by looking at the picture. So what this thing is going to do is just the same. I mean, what this experiment did is that they have a tracker I described before. This is a muon tracker. So muons come from above the pyramid, and you just trace the trajectory of every muon, and then you map and you look for regions where you get more muons than you would expect if the pyramid was completely solid. And you get more muons, that means that in that direction you have less matter, and that you can have a cavity. The next one, please. So our detector is actually built, it resembles that of Luis Alvarez. Of course, I mean, this is an experiment carried out by some 40 years later. So our experiment just profits from late technology. The detector was built entirely in Mexico, and was inaugurated, well, it was assembled 2 years ago as a piece of equipment, and I'm going to describe the state in which it is right now. This is a picture taken from our rector at the time of the presentation. This is the director, or used to be the director of the Anthropology Institute at the time. This is, I think, today is the most well-known Mexican experiment in particles physics experiment in Mexico, and it has been reviewed by the most important scientific journals. The next one, please.